Right. Thanks for being here this morning, and thanks for the lovely introduction by Michael. This first talk is really it's the first of two halves. So later in the week I'll give the second half, and I'm hoping to rush through some of the most basic concepts in this first half, and then dive somewhat deeper into what I consider to be the cutting edge on this topic later down the line. When you remember Michael's slide, he was saying that this workshop is about, the principles of uncertainty for quantification and experimental design. I'm not going to dwell on experimental design, even though it's a topic I've recently become quite interested in, but I know that you'll be in capable hands with Desi taking over from there. What I'll instead talk about is Bayesian inference, and I won't just go through the basics because I assume if you're here, then you have at least passing knowledge of Bayesian inference. And instead, what I'm trying to drill down on is the kind of efforts of the community to modernize some of the ways in which we do Bayesian inference that are relevant for modernizing Bayesian inference for machine learning and also experimental design. And so when I do this, obviously, there's quite a limited perspective here because I'm the speaker, and it's quite a big word, and it's an even bigger area. So there's a lot that I will not be covering. I will be covering my perspective on these issues and what I think are the most interesting perspectives on this. Okay, if any of you were in Singapore last week for BaseConf, by the way, this is the same talk I gave there, so you're free to leave. Please don't feel like you have to sit through the same thing twice. Okay, so, right, I said I'm not going to cover Bayesian inference in detail, but I think, let's establish some ground rules, what we're actually talking about. When people talk about Bayesian inference, they often make reference to Bayes' theorem, which is a component of Bayesian inference, but not everything, because Bayes' theorem is just a conditional. It's just a mathematical truth about the inversion of conditionals. It doesn't actually tell you anything about how you should learn from data, whether that's in an experimental design framework or otherwise. In order to learn from data, you need to translate this mathematical truth into something that is a bit more frail. Namely, you need to take your conditional probability, make it into a model on the data, have it indexed by a parameter, and then specify some kind of prior distribution or prior belief that you have about which values of the parameter indexing that model you've used to describe the data. And in particular, that prior should reflect what you think are good descriptions of the data. And then when you compute that conditional, so if you invert the probabilities, you arrive at what people call the base posterior. And we all love this object because it averages over models. It allows us to quantify our uncertainties. So that was one of the big points Michael made earlier, that we really want to think about uncertainty quantification. Much of this talk will be about new ways of thinking about uncertainty quantification that go beyond just inverting conditionals. And then lastly, the prior is attractive, especially for something like experimental design, because it allows you to include any domain expertise you may have. Especially if function evaluations are very expensive, that's quite important. And one of the sort of, classic applications of this, specifically at the intersection between statistics and machine learning, is the Gaussian process, which sort of gives a very neat overview of all these advantages. You're averaging over models. As you observe more and more data, as you evaluate your function, you collapse around the true latent function from which you observe data. And you can see here this GIF animating what I think a lot of people think about when they hear Bayesian inference. Now, Bayesian inference is really powerful, and if it works well, there's really nothing to be fixed at the foundations. However, for it to work well, you often have to make a number of assumptions that are quite problematic, specifically if you're dealing with high-dimensional data, noisy objects, really complicated problems you're trying to solve, because necessarily you have to make some simplifications. And the first of these is that in order for Bayesian inference to produce uncertainty quantification that is calibrated in a meaningful way, you need to assume that your model class actually contains the truth. So we need some kind of parameter vector theta star which recovers the data generating process, at least approximately. And when I say approximately, it has to be pretty good for the uncertainty to be meaningful. One of the immediate ramifications, if this assumption holds, is that now the only space that you need to care about is the parameter space. Why is this important? It's important because one of the ingredients of Bayesian inference is actually the specification of the prior. And the prior, if you come from it using a decision theoretic lens, which is often what people use to justify why you should do Bayesian inference, when you come at it from a decision theoretic lens, the prior really should express your prior beliefs about the true state of the world before you see the data. You can only do that on a parameter space if the parameter space contains all relevant states of the world. And so this is why assumption 1 and assumption 2 are quite important and have an interesting relationship between each other. You need to be able to specify a prior, but you're really only doing that on the parameter space. So the parameter space needs to be the relevant space about which you make your prior beliefs known. Another thing that's sort of tangled up in the second assumption is that you need to be able to write down what you believe about the true state of the world in form of a probability distribution, which we actually know experimentally is quite difficult. Like if you ask people to write down what are your beliefs about the heights of people in this room, they're pretty terrible at writing down a probability distribution. We don't really reason probabilistically. So actually eliciting priors is quite challenging in its own way. And then lastly, the third assumption that a lot of this workshop I'm sure will revolve around is actually computation. Because it's all fine and good if you write down a conditional probability, but unless you have means for computing it, it's not very useful. I'm not going to go much into this third assumption because I think it's been covered a lot elsewhere and there are other people who know much more about this thing. But it is one of the assumptions that you have to impose in order to make sense of what Bayes' rule actually tells you if you want to learn from data. Okay, so in the context of machine learning, modern problems, we have arrived at a place where we have so much data and the data is really complicated and these simplifying assumptions are actually quite fragile and lead us to bad outcomes. And I'm going to walk through an example that kind of showcases why these assumptions weren't problematic in the before times and are now somewhat difficult to deal with. And I'm going to start with a kind of, the vanilla base case that you're going to learn about in Stat 101, when they tell you what a statistician does, or at least what I was told what a statistician does. The reality looks quite different, and I think probably looked quite different even in the before times. But at least this was a description of reality that was somewhat amenable to reality. Okay, so in this idealized world, it's a bit like the Disneyland of the statistician. There is this expert that has a very clear research question. And in order to answer the research question, they carefully design an experiment, they collect their data, and then they approach you because they admire your expertise. And together you sit down and you work out a model and you work out a prior. Now all of this is idealized, but at least it's conceptually plausible that this might happen somewhere. And so you write down the mathematical model that should describe reality and you try to elicit these hard to elicit priors from the experts. If you've ever worked particularly with doctors, medical experts, you will know how difficult it is to do that. And then once that's done, you just give them a link to a GitHub repo and run their favorite MCMC algorithm that's appropriate for the model class that you have settled on. One example where you can actually see this live in action is this paper from the late 1970s by two labor economists. Oh, sorry, not labor economists. I think, well, anyways, they're economists. And they were asking the question, what is the influence that air pollution has on housing prices in the Boston area? Quick show of hands. Who of you has worked with the Boston housing data set in a machine learning paper? Right, okay, so this is actually the origin of that data set. So it came from a very clear research question. And in order to answer their question, these people came up with a very fine-tuned model that was trying to respect what people knew at the time. It was also in alignment with economic theory, at least at the time. And it looks very simple, but actually, if you read the paper, it's like 40 pages of descriptions of how they arrive at this seemingly simple model. It's very clearly structured. There are some parameters that tell you what you want to know. There are some parameters that just control for effects you may want to not bleed into other parameters, and so on and so on. Very classical statistics. And so the model here is actually fairly well specified in the sense that a lot of thought has gone into it. It's not necessarily a complete characterization of the truth, but at least an attempt was made to characterize what these people believed to be the truth of the world. Likewise, the prior that you can specify in this case is actually not too difficult to do. I mean, it's still difficult to elicit priors, but at least you know what your parameters mean. So in principle, if you scour through the literature in economics and you assume that people are somewhat literate, you can probably compile priors that are a reasonable expression of what the field knew at the time. And likewise, this is just a linear model, so actually computation is not a big challenge here. And so the three assumptions we started with are actually not that problematic in these kind of settings. This changes a lot once you enter the domain of large data, complex models, and machine learning. Because what people do in particularly Bayesian machine learning, if you actually read the papers, is they start with a model. There isn't a research question, there's a model. And then that model is applied to multiple different data problems, and you kind of measure the performance. And I would wager that most of you who have seen the Boston housing data set have seen it in this context, where someone has used the Boston housing data set as one of 10, 20, 30 examples to show that actually, predictively, the error you make is reasonably small. When you do this, obviously the model you specify is a much more complicated object, and as a consequence of this, the inference becomes a much bigger part of the puzzle, because you need to do inference for more parameters, everything becomes more complicated, and actually you need to compute things in time, which is why in Bayesian machine learning a lot of emphasis is actually placed on approximate inference schemes. And this is entirely a function of how you set up the problem. And just to give you one example of many, so this is a 2020 paper from AI Stats, which also relates to the Boston housing data set, except here, they start with a model. The model is, unsurprisingly, a deep neural network, and we'll hear more about how these models work for scientific discovery later today. So they're very useful, and they probably can recover the data generating process accurately for some parameterization. It's a bit more difficult to figure out what that parameterization would be, and it's even more difficult to figure out what your prior belief over these parameters should actually be. And one of the chief reasons for that is that these parameters are no longer interpretable. So actually, even though we call these things parameters and we call these things parameters, they actually have very little in common with one another. And arguably, you should think about this as a non-parametric model to begin with. Okay, so actually specifying the prior is really hard. And so in this particular paper, they just choose a Gaussian, because otherwise there's no hope of you actually computing this object in the first place. And then despite the fact that the prior has been compromised to do anything in terms of computation, you still need to approximate the resulting posterior. So actually, you've got two compromises in this specific example of the principles we've laid out that were quite appropriate for the standard Bayesian case. Okay, so we've seen that there were a set of assumptions that are reasonable for some problems, and these problems still exist, by the way. I mean, if your data collection is really expensive and you grow something in a lab and you have 25 cell cultures, you may well be in this setting still. This is not a setting that's become obsolete, but this is a setting that makes assumptions that are inappropriate for a lot of machine learning problems we face today. And so in that setting, what served us well has no longer got as much value as we would perhaps like it to. And so there's this community of people that have kind of identified this problem, and I'm part of that community. And the name we've recently given ourselves, even though this is just a label, it doesn't really mean much, but the overriding question is whether we can keep the benefits that we associate with Bayesian methods and that we like about Bayesian methods without necessarily having to rely on these assumptions. And so in particular, what we want to do is we want to quantify uncertainty by going beyond Bayes' rule as the epistemological principle. And so there's a little attempt at the moment for us to build a community together. So if you're interested in this, there is, in particular, I'm going to skip over this, there was a workshop recently, but there is a seminar happening every 2 weeks where we cover these kind of topics. If that's of interest to you, you can send me an email afterwards and I can tell you where you can sign up. Or you can just Google Post-Bayesian seminar and you'll probably find it. Okay, so when I say Post-Bayesian Inference, or when I say people want to go beyond Bayes' rule, what do I actually mean? I like showing this slide. I think it's quite educational. The way I like to think of what it means to go beyond Bayes' rule is you conceive of the space of possible belief updates, which is ultimately what you're trying to do when you do Bayesian inference. And you look at the Bayes posterior as a particular element in that set. And then you ask the question, how can I explore, how can I traverse other areas of this space? And the simplest answer, and the first answer people came up with is they said, well, we could just take the likelihood, and if we are worrying about the likelihood being misspecified, we could try to temper the likelihood, right? We could try to make it have fatter tails. And a very primitive way of doing this is you raise it to a power. When I say belief updates, as you can see up there, what I mean is that you map from a prior and some data back into the same space from which the prior came, which is your posterior. Okay, so the first idea people had is they could say, well, we could raise the likelihood to a power. And if you do this, what you end up with is something that was explored in depth in the 2010s, in particular by Peter Grunwald. I spoke with Peter recently, and good news, he agrees it should be attributed to him. So you raise the likelihood to a power, okay? This is no longer a likelihood, normally. So when you integrate the likelihood with respect to the data, this is no longer necessarily 1. In fact, it need not even integrate. So sometimes people call this a pseudo-likelihood, but bear in mind it's not actually a likelihood. And it's not even necessarily an unnormalized likelihood. Either way, once you do this, the idea of this is that you downweight observations that happen in the tail. And what you do is you kind of explore a slightly bigger space in this set of belief updates. And interestingly, this sort of configuration has popped up in sort of more traditional statistics, thanks to Peter Grunwald, but also more recently in more hardcore deep learning, people have started realizing this is quite an interesting object. And there, I think it's called the cold posterior. So if you've ever read about the cold posterior effect, that's basically what this is. And interestingly, actually, the direction of the choice of learning rates, which is what this lambda is sometimes called, is exactly the opposite in the statistical literature to the cold posterior effect literature, for reasons that maybe I'll get into later. Anyway, so you can do this, but you're quite limited in the range of options, because all you're tuning is a scalar parameter, and in particular, if you're trying to do inference on 1,000-dimensional vectors, this is quite a limited lever. You'd like something that's a bit more brute force. You'd like a bigger bazooka. And so very soon after this became popular, people started, just saying, well, why don't we just replace the likelihood with something else that measures how well the data fit a particular parameter. And one way of doing that, that's quite universal, is a loss. And so you could just replace the likelihood function completely with an exponentiated negative loss function, which again, sometimes people refer to as a quasi-likelihood or a pseudo-likelihood. And if you do this, you arrive at something that's often called the Gibbs posterior. It's also called generalized posterior, quasi-posterior. Again, has many names. Here I give you the reference of Basiri, Holmes, and Walker. This object predates 2016, but this 2016 paper gives a really rigorous justification for why this is an object you may want to study for doing inference. And it's quite foundational in this specific area. Okay, so that's a Gibbs measure. Now you have like a lot more power, and you can do a lot of interesting things with that. But there's still some things you cannot do, which is why we extended this further in the early 2020s. And essentially, what you can show is the Gibbs posterior can be recovered as a particular solution to a variational problem. And once you write down the structure of that variational problem, you can see that it essentially trades off a data fitting term and a prior regularization term. So it prevents you from going too far from the prior, while at the same time trying to fit you to the data. And you can extend this logic further and obtain something that we call optimization-centric posteriors. And we'll cover these objects and also some of the properties of Gibbs posteriors in the second part of this selection. Lastly, I want to mention this, even though I'm not going to cover it today, there is a completely different form of generalizing Bayesian inference that is more recent. So you may have heard of martingale posteriors or predictive resampling-based approaches. And what these approaches do is they essentially use Dub's theorem to show that you can recover the base posterior by predictively resampling using the base posterior predictive, and then they extend this logic by arguing that as long as you have a predictive resampling scheme that has particular properties, in particular the martingale property, you can actually still do something similar, and you obtain a notion of uncertainty where you've specified the prior on your parameter implicitly by means of how you've constructed the predictive resampling sequence. If any of you were here for Sonia Petrona's talk, this is basically her area of expertise. So if this is interesting to you, I would point you to her talk at the previous workshop. This is also something that we're currently discussing at the seminar I flagged earlier. So this is Edwin, who is one of the chief architects of this area of research. So if that's interesting, you can learn more about that, and the talks are also recorded online. Anyways, I'm not going to talk about that. I'm going to talk about these three other objects in these two parts. So I'm going to talk about the power posterior, the Gibbs posterior, and these optimization-centric posteriors. I'll do that in three parts. Okay, 1, 2, 3, and these numbers will be in the top right corner if you get lost. For the power posterior, what I want to focus on is to structure it according to questions. Okay, so we're going to ask a question, and then we will provide an answer. And in particular, the first and most obvious question is, what does this actually do? Like, why do people care, and why do they do it? And then I want to quickly go through some of the discoveries we have made in relation to this object, and why people have actually started going beyond that, why it's not enough, why we need a bit more, and why we need to use Gibbs posteriors or optimization-centric objects instead, if we really want to have the full power of what we're allowed to do once we abandon Bayesian principles. Okay, so what does this actually do? I mean, it's fairly straightforward, right? If you look at the parameter lambda, you can see that as this parameter increases, you get more and more weight to the data. Eventually, you would end up with essentially a point mass at the maximum likelihood estimator. But as the lambda goes to 0, you essentially just recover the prior. So this allows you to interpolate between a posterior that is completely identical to the prior to something that is essentially recovering the maximum likelihood estimator. So fairly straightforward. Doesn't sound very interesting, so the natural follow-up question is, why do people do it? And so this is really down to the discoveries by Peter Grunwald and his colleagues, who discovered that in particular settings of misspecification, this can really help you out. So imagine you have some kind of misspecified simple model in this case, so let's say it's a regression model, and you look at the squared predictive risk produced by fitting parameters to this misspecified model. What you end up with are these curves. Now, each of these curves corresponds to a different method of performing inference. And what you can actually see when you assign labels to these different curves is that the two methods that perform the worst are the base posterior and the maximum a posteriori, which is just a point estimate that takes the point of maximum density in your base posterior and uses that as a plug-in estimate. And you can see you get large excess risk relative to other approaches when you do this, so long as your data relative to the number of parameters you use is small. Okay. So in the small data setting, I'm going to say small data setting, but it's always relative to the number of parameters. In the small data setting, this gives you poor predictive performance. And you can actually address this by choosing a value of lambda that is, they give you an algorithm for choosing this that I'm not giving here because it's quite complicated. But there is a way in principle you can choose this lambda adaptively so as to avoid this excess risk. Now, what's quite visible here as well is that actually this is only a small n effect. So as n increases, you can actually see that this effect vanishes. So the answer to why would you do this, why would you use a power posterior to improve your predictions, is you would do it to improve predictions if and only if the number of observations is small. And so obviously immediately it raises the question, what should we do if the number of observations is actually moderately large? Can we still actually use this to this effect? And essentially the answer is no. So if we write down the posterior predictive that integrates out this power posterior, okay, so here we have our likelihood model and we're integrating out the uncertainty in the parameter with this power posterior. If we take this posterior predictive and we construct a hypothetical optimum, so it's this lambda star here which minimizes some kind of discrepancy, let's say it's the total variation between the true data generating density and the predictive induced by this posterior predictive. If you do this and you try to minimize this over lambda, what you actually find is that the curves you obtain look like the thing I've plotted up there. So you can see they flatten out. And in particular, there's actually no unique minimum. And this holds whether or not you look at them in expectation. So you can imagine computing this for one fixed sample from Q for which you compute this predictive, or over many, many samples. Either way, the curve is flat. Which means, okay, so just for your orientation, this is what the prior predictive would give you. This is the posterior predictive at lambda equals 1, right? And this is the plug-in predictive as you push lambda all the way to infinity. So that's the maximum likelihood estimate. And what this tells you is that actually this lambda star is ill-defined. So if you tried for moderately sized numbers of samples to choose the lambda to optimize prediction, it doesn't work. Because actually, eventually, the maximum likelihood estimator is basically as good as any power posterior with a sufficiently large lambda. And so what this means is that while we can use power posteriors for very small sample sizes, actually the benefit they provide vanishes if you have too many data points. Okay, what else have we learned about these objects? There's actually some theory on them that's quite interesting I'm not going to go into, but essentially they have regularity conditions that standard Bayesian posteriors do not have. You can also interpret them in the vein of what is called coarsened Bayes. Coarsened Bayes is an idea where instead of conditioning on data, so you're still using conditional probabilities, but instead of conditioning on data, you're conditioning on a neighborhood of the data. So you're coarsening where the data actually occurred. You can, however, show a few drawbacks to this as well. And the first of these drawbacks is that it's in general very difficult to choose this lambda. So I've shown you how it's difficult to choose them if you want to choose it predictively, but there are some other objectives you might want from this lambda. It doesn't really matter what objective you want, it's quite difficult in general to choose them. And the objectives you pick often deliver very, very different lambdas. So it's actually not clear how you should set this learning rate to begin with. And the other problem is, so the predictive benefit vanishes as the number of observations increases. But also actually some of the other benefits of this lambda vanish as the number of observations increase. So one of the main reasons why people have studied this is robustness. And you can actually show that this also goes away if you observe more data points, because the entire point of this object is that it gives you robustness by placing more weight on the prior. And the prior vanishes as n goes to infinity. So actually you get none of the robustness benefits for sufficiently large n. And this is one of the reasons why people have started going just beyond power posteriors and have looked at Gibbs measures instead and optimization-centric posteriors. Okay, so let's summarize quickly. What does this do? It trades off the prior against the data. Why do people do it? Classically, to improve prediction in small sample sizes. But we've also discovered that there are some severe limitations in doing this, namely that actually, as long as your sample sizes are moderately large, it doesn't improve your prediction, and it doesn't actually improve your robustness either. And so that's why people have chosen to go beyond it and have addressed, Gibbs posteriors or optimization-centric objects instead. Should we take questions here? I think that would be best before I move on to the next part of the talk. I'm very happy to do that now. Yes.
Great talk so far. So the word misspecified is often overloaded. I'm not singling you out here, but I'm just curious to try to understand what you mean when you say misspecified, because the misspecification that often results in theoretical issues is when the support of the prior actually doesn't contain the ground truth parameter settings. And perhaps that sort of misspecification is actually less bad in modern machine learning, where we're building these really massive models that are very expressive. Misspecified can also mean that the prior doesn't entirely reflect the reality of what we're trying to model, but in that sense, everything is misspecified, including the classical statistical models that we were sort of thoughtfully and transparently developing decades ago. So I'm just kind of curious to understand what you mean and what you think about that.
Yeah, no, it's a good point. So, I mean, one of the problems with this terminology is that it comes from mathematics. So everything is binary, right? The model is well specified or misspecified. In practice, as you know, you're kind of on a continuum. And one thing I would say, as it relates to whether you don't have these problems in machine learning models, I think this is a really interesting point, because essentially you don't have this problem in the model class because you can find a parameter vector that recovers whatever you want, but you're kind of shifting the problem into the prior. And so I think actually in a lot of these deep learning models, the problem is more pronounced in prior misspecification, or what the prior actually does, because you have given yourself so much freedom and flexibility in the model class you've specified that now the prior has to carry all the weight. And so I think a lot of classical statistical insight in this isn't very useful, because we're thinking of small models where actually all the hard work happens in the model class you specify, and the prior is kind of an afterthought, and you can normally bleed out any problems in the prior as you get more data. And I think that's really why we haven't found a good grammar for talking about these problems, because you kind of really need to think about the joint effect of prior and likelihood, but the maths we're using doesn't currently accommodate that. I don't know if that answers your question, but...
Partly. So in this broader sense, would you say that every model is misspecified, at least to some extent, then?
Yeah, I mean, that's in the binary sense, that's always true, right? I think the question is...
There's sort of a spectrum.
Yeah, yeah.
Models lie in different parts of that spectrum.
Yes, I think this is a difficult question to ask. I think, yes, in principle, every model is misspecified unless you generated the data on your computer, but I don't think that's a necessarily useful distinction in practice, right? So if you run a model that's misspecified knowingly and it still works reasonably well, it's because the degree of misspecification isn't practically meaningful. I think that happens all the time, right? Like even in physics, where people think of models that are very carefully calibrated, they are just approximations of the truth. So they're still wrong in a technical sense, but nobody cares because the degree of error is so small that you wouldn't care. And I think one of the challenges in machine learning models is that it's really difficult to actually make this statement, to say this model is misspecified, this model isn't. So I wish I could have a better answer for you rather than waffling around like a politician. But I think the honest answer is that I don't think we have the tools for honestly answering your question. I think that's just one of the limits of our knowledge at this moment in time.
I have a question out of curiosity. So for many statistical models, there are small sample biases. For example, for autoregressive model, if you have a very small sample size, your estimation will be biased because of lack of information. Do you think this kind of power posteriors can solve the problem of lack of information? Because it seems like it can magnify the information from data set.
So yes and no. So it can magnify your information, but the information has the same coarseness, right? So if I scale up the lambda, let's say I take the lambda to be equal to 2, I'm just double counting all my observations. But if I have a bias with lambda equal 1, so if I count my observation 1, I have the same bias if I count them twice, and maybe the bias is worse. So what the lambda allows you to do is allows you to trade off the effect of the prior and the data. So if you're very worried about, let's say, the bias that the data induce, if you think that your prior is very good, then actually giving more weight to the prior gives you kind of robustness against the badness of the data. But conversely, if you actually worry that the prior is really bad, then you should probably give more weight to your data. So this is one of the reasons why I don't necessarily like the framing of these power posteriors as robust objects, because if your prior is garbage, then downweighting the influence of the data is not good. And so, for example, going back to machine learning models, right, that's why people in cold posteriors, they use a lambda that's very, very large, because a lot of the information comes from the data, and actually specifying priors is more difficult. Whereas in these more classical statistical settings, it's exactly the other way around. I don't know if that answers your question, but yeah. Sorry, there's two questions. Michael, you want to go first?
Okay, thanks. Just a quick question about like some slides back where you had the curve where we have the TV. Yeah, exactly there. So is this a theoretical result or was that from an example?
So this is actually from an example, but you can show basically formally that curve. So you can't show that the region is always flat. But what you can show, so there's theorems in the paper that show that essentially exponentially quickly the difference between the plug-in predictive and the power posterior predictive as n increases goes to 0. So there is some theoretical backing to this. There are important caveats. So I've shown you here a continuous example because the curves look very nicely. It's a bit more tricky with discrete data. So if you observe like a Bernoulli model, there are actually very strong arguments for never using the plug-in predictive because you have these boundary problems in the maximum likelihood estimator, right? If I flip a coin twice and it's heads both times, it's well known that the MLE does rubbish. So in those settings, you can show that there is a unique minimum, but it vanishes extremely quickly. So like even if n is 100, it's already gone. So it depends, but discrete data are tricky, but for continuous data, I think this is probably a representative figure, at least under the conditions we impose in the paper. Yeah. Sorry, I think Desi had a question as well.
Following up a bit to Andrew's question, actually. So have you thought about kind of the role of non-identifiability, right? So you have a huge model class that surely you can can't we say that, you know, the model is not going to be specified, but they can't identify it. So yeah, I'm just wondering what your thoughts on that are.
So what's the question? So have I considered identifiability for what particular aspect of this?
I mean, how that aspect relates to the fact that sure we're using these super large machine learning models, in that then we claim that, you know, they will cover our like large enough hypothesis class so that we can be, you know, moderately sure that, you know, the model is not going to be specified. But then, you know, at the end of the day, you probably wouldn't be able to identify the parameters from the data that you have. And, you know, how does non-identifiability kind of enter your framework that you're sort of describing here?
Yeah, so it doesn't enter the conceptual framework, but the moment you try to prove anything, you kind of need a degree of identifiability. It's really difficult to prove, including these results, by the way. So, I mean, we can really only prove this if the model, so it's not technically identifiability, but something like that you need for these results to be meaningful. So it's also like a big leap for me to say that these results are actually meaningful for the like cold posterior case. It's possible that this completely misses the mark. And that actually what's happening there is quite different qualitatively from this. I think that's one of the limitations of the mathematical technology we're currently working with. It's really difficult to make the kind of statements we would like to make if you need, if you need to account for model non-identifiability. Sorry, Andrew, I think you have a follow-up to that as well.
Oh, sorry, yeah, just a very quick comment as well. Like, for the cold posterior effect in the big, deep models, quite often this was also observed as an artifact of data augmentation combined with SGLD inference. So if you do data augmentation with SGLD, you end up kind of multiplying or dividing your likelihood, raising it to a power of, say, 1 over k, where k is the number of mini batches. And so tempering just sort of counteracts this. In some sense, data augmentation actually made like the posterior too diffuse, and tempering sort of sharpens it up to kind of like a more reasonable thing. And so in this sense, actually, that effect could be observed in classical statistical models as well that are very simple and transparently specified.
Yeah, thanks. It's obviously a literature you know much better than me. Okay, do we have more questions? I think Michael's giving me the nod to move along. Okay, I'll do that then. Okay. So that's why people kind of started looking at Gibbs posteriors, because you know if all you get to play with is a parameter lambda, that's a scalar, that's probably not as interesting. And so for the Gibbs posterior case, we have to answer a few questions. We have to answer why do we do it? So we've seen the drawbacks of other stuff, but there's probably hopefully some constructive reasons for why we would do this instead. We're going to ask how we should interpret them, which actually is quite difficult. Like interpreting the uncertainty that comes out of these objects is no longer a conditional probability, not even close to it. And so you kind of need some other conceptual devices. We're going to ask when they are robust, and here I'm going to talk about robustness strictly in the sort of Huber contamination sense of the likelihood model. Okay, so it's going to be fairly rigorously defined. And then we're going to ask how you can actually design these posteriors to be robust in that Hoover contamination sense, and how they can be computed, or what kind of hurdles or strategies are new when we compute Gibbs posteriors rather than standard Bayes posteriors. And so to sort of kick off why we would want to do this, here's a GIF produced by Gerardo. Obviously, you know, I'd be way too lazy to do this, but he did this amazing GIF where we have essentially an application of Gibbs posteriors to Kalman filtering, where you can see if you've got outliers, the standard Kalman filter, which you can understand as a Bayesian object, it really lacks coverage of the latent signal. So you can see as you get more and more outliers, this green line is like really distracted from these outliers, and it fails to recover. And you can essentially fix this by modifying the updating mechanism. So this is still an exact update of your beliefs, but it's no longer a Bayesian update of your beliefs. You can, by the way, do all of this in closed form, so there's no MCMC sampling going on here. This is very tractable. And now you suddenly track this signal rather closely. Okay, so this is the answer as to why would you care? You can actually solve some real-world problems with this. And in particular, you can solve outlier problems that you may not be able to account for in other ways. Whenever I talk about outliers, people like to point out that you could be able to remove these outliers before you actually run the algorithm, and sometimes that's true, but actually this becomes quite difficult if you deal with higher dimensional data. And higher dimensional here doesn't mean hundreds and thousands of dimensions. Actually 10 or 20 is enough for this. It's really difficult to identify outliers in high dimensional spaces. And in fact, talking about model misspecification, in high dimensions, you can basically show that any model is immediately misspecified because the density is spread so thin that everything essentially becomes an outlier. So there's some technical findings to this effect as well. Okay, so simplifications that I might apply throughout the talk. So you don't have to specify the Gibbs posterior in relation to a statistical model. I just think it's the most interesting case. This parameter theta could be in relation to any arbitrary parameter. For example, it could be the median of your distribution you care about. But I think the most interesting case normally is when it comes from a model. And likewise, the scaling parameter also appears in the Gibbs posterior. I'm not really going to cover what problems that imposes, and I'm often going to suppress it for notational convenience. But here you go. These two simplifications I will make throughout the rest of the talk. Okay, so how should we think about these Gibbs measures? There's kind of two perspectives on this. And the first of them is the general Bayes update perspective. So the idea here is that you can rewrite, at least under conditional independence, you can rewrite the likelihood as a product. And because you can do this, you can update the posterior after n observations as the posterior after n-1 observations with the next likelihood term. Okay, that's basically the phrase that today's posterior is tomorrow's prior in one line. And the question people asked is, how can we extend this logic beyond likelihoods? And that's really what the Basiri, Holmes, and Walker paper did. And they basically figured out the key ingredient for doing this are summable losses. If you have a summable loss, this kind of general Bayes update still holds, where now you replace the likelihood with what they call a pseudo-likelihood, or an exponentiated negative loss. And really the only condition you need for this is summable losses. Okay, so, I guess the slides are in the wrong order. Anyways, so the main restriction of this interpretation is that you need summable losses, which is not necessarily very restrictive, but sometimes you do want to go beyond it. If you do want to go beyond it, or maybe if you just want to have like a second way of viewing this, you can also see Gibbs posteriors as essentially trading off a linear loss in Q with a convex loss in Q. Okay, so the linear loss is essentially just an average over this loss function L that we've discussed. And the convex loss is the Kullback-Leibler divergence between the Q you're trying to fit to the data and a prior that prevents you from drifting too far from your point of origin. And this minimization problem is defined over the space of all probability measures. It's actually very easy to prove this exactly if you want to do that at home, if you want to have fun. What you need to do is actually just rewrite the right-hand side as a Kullback-Leibler divergence itself, and then you know that the KL is minimized if and only if both arguments are the same. So it's quite a nice proof. I really like it. Anyway, so that you can do, and then you no longer need the loss to be summable. The role of pack-Bayes, so if you know this sort of elbow formulation in this form, so normally in a lot of ML, they write the elbow slightly differently sometimes. But if you've seen it like this, likely you have seen it in pack-Bayes. And pack-Bayes uses these kind of minimization problems to ask the question, what kind of generalization guarantees you get out of Gibbs posteriors. So Gibbs posteriors actually emerge organically out of pack-Bayes, which is why people in the pack-based community will sometimes say, oh, there's nothing new here, we know all this. And I think it's true to an extent. There is nothing new in the sense of how we write down these objects, but actually the question we ask about these objects are to some extent new, because pack-based also doesn't care about anything really other than generalization guarantees. And in the more statistical perspective on these Gibbs posteriors, we do care about a lot more. So for example, we care about robustness, as I was mentioning earlier. We ask how we should design these losses. So again, in pack-based, normally these losses are God-given to you. And we also care a lot more about asymptotics, which again is kind of irrelevant for pack-based, because pack-based cares about finite sample guarantees that are, ideally optimal. So I would say that the questions are related, but they're not the same. Okay, so the remaining 15 minutes, I think I will focus on the robustness question. So I want to ask, when can we make these Gibbs posteriors robust? And hopefully I'll get to cover why or how we should design these losses to be robust. And then we can cover the remaining questions in the second half of the talk on Thursday. Okay, so when are these objects robust? To define robustness, and this goes back to Andrew's question earlier, we are going to be careful about what we mean by robustness here, and I'm going to talk about Huber robustness. Okay, so Huber robustness means you have a kind of data generating distribution, which is this Q epsilon. It's subscripted with an epsilon because a component epsilon of the distribution comes from some kind of contaminant, which I'm writing down as C here. But the overwhelming majority of the probability distribution actually comes from something that we can model. So this Q0 here, this golden distribution, is something that you can fit using the model that you have posited. In practice, what this looks like is this. Okay, so you have kind of a histogram that comes from your blue distribution. You have a kind of contaminated area in that distribution, and you're hoping not to overfit your inferences to that contaminant, because what you really want to do is you want to ignore that, and you want to just model the bulk of the data that you can describe, in this case with a unimodal Gaussian distribution. I'm not saying this is always what you should be doing, right? Certainly in this example, you can actually identify that there's a contamination. You probably should use a bimodal model, but as I was mentioning earlier, in higher dimensions, you don't even see these contaminations anymore. You've got no way of even plotting them necessarily. Okay, so if you just fit a standard Bayesian procedure to this kind of data, what you end up with, if you have a Gaussian model, is this black line here, and that's what we want to avoid. Instead, what we want is essentially whether or not we sample the data from the contaminated or uncontaminated distribution, we want the posteriors that we compute to be roughly the same. And now we need to make that roughly the same a bit more concise. What we actually want is some kind of distance between the contaminated and uncontaminated posterior, and we want that distance to be at most linear in epsilon. Now, obviously, that distance will depend on some constant, and that constant is a function of the nature of the contamination. The reason, by the way, why you want this to be linear in epsilon, there's like a very long history of robust statistics going all the way back to the 60s and Huber, and I don't have time to go into this, but trust me, basically, this thing should be linear in epsilon, okay? This is what you want. Now, what I've shown you here is not good enough. Why? Because in principle, you can now choose a sequence of contaminations to make the right-hand side go to infinity anyways. So the fact that it's linear in epsilon doesn't mean anything if you don't control for the constant here. And so that's why really what you want is the supremum distance. So you want the supremum over all possible contaminants of this distance to be upper bounded and linear in the size of the contamination. And once you impose this restriction, it becomes very natural to work with this supremum distance between densities. So you can essentially think of this as looking at the two densities, and then at each point in the parameter space, you track how different they are from one another, and you take the maximum distance between them. This is quite a crude measurement of robustness, okay? Like this is not very refined, and therefore this measure of robustness is too conservative. It would tell you that the Gibbs posterior is not robust in some situations where it is robust, because this is a crude measurement. But it is quite computable, because what you can show is if you work with this, the key quantity actually becomes a version of the loss. Now, let's backtrack here a second. Why is this important? It's important because the distance we have defined is between posteriors, which are infinite dimensional objects. So we have made this simplification here to project this problem into Euclidean space. So suddenly, we can actually deal with this. And in particular, we can essentially show that what we need to consider is the sensitivity of the loss to contamination. And when I say sensitivity, I'm talking about the derivative. The derivative with respect to the size of the contamination. If you look at the right-hand side here, you're looking at the difference between the uncontaminated and the contaminated loss, scaled with the size of the actual contamination. And as the epsilon goes to 0, you get the sensitivity of the loss to contamination. And what you can show is if that sensitivity is bounded. So if the loss doesn't arbitrarily explode in particular regions of the parameter space as you get a tiny bit of contamination, then that loss is robust. And if this loss is robust, then you can show the Gibbs posterior is robust in this specific sense. Okay? And so this is quite elegant because it's quite a universal way of proving that if I give you a loss, that loss is or is not robust. And in particular, it does so making reference only to a Euclidean object, which is this loss. And so this is a neat trick that we developed in the early 2020s, and that's now kind of a staple of this literature. I think there's some more work to be done using a distance that is more refined, but for now it's the best we've got, and it is quite effective. Okay, so the Gibbs posterior is robust whenever our loss is, and it's worth noting that you do not in general get this condition for log likelihoods, which is why we bother with Gibbs posteriors in the first place. Okay, if this were true for log likelihoods, then a lot of what people have worked on in this area would kind of not be interesting or relevant. Okay, so I've shown you for an abstract loss how you can show robustness, but it's not really clear how you actually design these losses. Like, where do I find these losses? They don't grow on trees, so I need to go and I need to hunt for them. Where do I go hunting? Well, one of the things I can do is I can realize that when I do standard Bayesian inference, I have actually specified a loss and try and think about the problems with that loss. And that loss is the negative log likelihood, which you can show corresponds roughly to an estimator of the Kuiper-Gleichner divergence between your data generating process and the model. And once you notice this, you notice that basically the key problem here is that the Kuiper-Gleichner divergence is well known not to be robust. It's quite a prickly little measure. So one of the things we could do is actually work things the other way around. We can start with a robust discrepancy. Okay, so we can hope that there exists a discrepancy out there, so that whether or not I sample from the uncontaminated or the contaminated data, the discrepancy has roughly the same magnitude. And if that's the case, then I'm hoping that if I can construct a loss that approximates this discrepancy, hopefully the resulting Gibbs posterior is also robust. And indeed, this turns out to be the case. And examples of this are the maximum mean discrepancy, alpha, beta, and gamma divergences, and Stein discrepancies. And so to just give like a quick example of this, with I think it's gamma divergences and beta divergences, what you can show in these cases and why they were really interesting to people when this literature kicked off is both gamma and beta divergences recover the base posterior or the log likelihood as a limiting case as their hyperparameters go to 0. And what that means is you don't have to worry so much about what the uncertainty means, because as long as you choose gamma or lambda, gamma or beta small enough, you can hope that the object is still behaving a lot like a base posterior, except now it's essentially excluding outliers, but without you having to do so manually. So people were very excited about these objects because essentially they were hoping it would give you access to an automatically robust base posterior that excludes the outliers for you without you having to do so manually. And in fact, it can work really well like that. For example, on deep Gaussian processes, so this is some work we did where essentially what you show is that you speed up deep Gaussian processes by making them more robust. And the way this works is that you just need fewer hidden layers to make them work. So you can see here the test negative log likelihood. So as you go left, the error is smaller. As you go right, it's bigger. And you can see the number of hidden layers either in the robust or the standard case and the error that they make. And when you look at this, is you can see that as you increase the number of hidden layers, you're actually performing better with fewer layers in the robust case. So you can see with one hidden layer in the robust case, you're performing as well as with 2 hidden layers in the standard case. And likewise, with 3 hidden layers in the robust case, or even 2 hidden layers in the robust case, you're performing better than with 3 hidden layers in the standard case. So the robustness here gives you like a very tangible computational benefit because it works. Okay, so why don't we see these gamma divergences and beta divergences everywhere? Actually, the question is quite simple to answer. And the reason is that I haven't shown you everything. Because when you look at these losses, they're actually intractable themselves. Okay? So they depend on integrals over likelihood models, which in general are intractable. For the specific case of a Gaussian, and in the specific case of the Gaussian process I just showed you, these are not problematic. You can actually work them out in closed form. But for general likelihood models, this is a no-go. Because essentially what you would have to do is, if they're not analytically available, you would have to draw some kind of sample from the likelihood model and then approximate this integral. And so this is why people haven't really used them in practice very much. Okay, so this brings us on to computation strategies. What can we do to actually target these objects. I don't know. Do you think I should take questions here and cut it short? Or should I?
Do you think you can cover it on Thursday, the rest of the
Yeah, I can cover the rest on Thursday. So we can just take questions here. Okay, so I'll leave it on this. I'll leave it on this note. We are now trying to make beta and gamma divergences work, and I will show you next week what we can do instead, or how we can overcome the computational problems we've introduced. Because we started out wanting to do things robustly. In so doing, we introduced a computational problem. If you remember the first slide, we had 3 assumptions. One of them making things computationally feasible was a desire. This is not computationally feasible. So we seem to be stuck. We wanted things to be robust, we've achieved that, but now it comes at the cost of making things computationally feasible. And so we'll resolve that on Thursday and other questions as well. And so I'll take some more questions in the remaining 5 minutes if we've got them. Yeah, Nicola.
Yeah, thanks. It's very interesting. My question, I think maybe you went over a bit fast, so I didn't pick it up. So when you have, like, let's say, a complicated posterior distribution, let's say in an example, in an experiment, which you don't really know what it's supposed to look like, and you're gonna say contaminate the data that you have to see if your Gibbs posterior is going to lead to more robustness or not. So what kind of do you look for in the experiment? Like, because you don't know what the true posterior is supposed to look like. So how do you assess, like, really, like, if your Gibbs posterior is giving you the properties that you want?
Yeah, so this is an interesting point, because I think there's currently a gap in the literature in regards to doing things on data. So the results I showed you are actually purely theoretical. So there's no data being used. I cannot evaluate. So actually, if you look at these robustness measures I showed you, one of the drawbacks of this entire supremum framework is that you cannot compute this in general. You can use this for theory to show that your Gibbs posterior is robust, but if you give me a data set and you ask me to quantify how robust is it on this particular data set, I can't answer that question with this methodology. So we're actually currently working on fixing this, because I think it's a big problem, where you can, you're basically blind to that question. I mean, one other thing that you haven't picked me up on, which you could have also picked me up on, right? This is a binary decision. The loss is either robust or it's not robust. But I mean, that can mean a lot of things. This thing could be upper bounded by 1 or by 10 million. Surely that makes a big difference for how this Gibbs posterior is robust. So to give you an example where this result is meaningless, I could use a log likelihood and then just say, whenever it exceeds 10 million, trim it off. That's not going to be robust in practice, but it would satisfy this condition, if that makes sense. So actually this theory, I think, is not sufficient for answering the kind of questions that you've asked, and we're definitely lacking that kind of informative theory for interacting with real data for a practitioner, and we definitely need that.
I guess that, like, you would try to come up with some metric, like, that tells you, like, the degree of
Yes.
robustness.
Yes, and then you need to prove that that metric, well, A, is computable on real data sets, and B, actually relates, hopefully, to this in some way, but is tighter. And so the way we're attempting to do this at the moment is that you actually compute a distance between discrepancies directly that is computable, and from which you can sample. So you make some concessions, but hopefully it's a useful metric of robustness that you can actually use in a given data set. Yeah.
Hi. I'm not very familiar with robust statistics literature, but I know in traditional robust statistics you have the M estimator, where there is always an optimal estimator of your model, but you kind of replace this optimal estimator with more robust ones, more robust loss functions. So can I understand this, like, the KL divergence here is the optimal estimator when no contaminants is in the data set, and now you're replacing this KL divergence with other kind of different divergence or discrepancy?
Yes, this is exactly what's happening. So there's the Bayesians are like 40 years behind in that literature. So a lot of what you're saying, the M estimator stuff, was developed in the 60s and 70s. And so there are all these clear trade-offs between statistical efficiency and robustness in the frequentist literature that we have no way of doing that at the moment. But that's exactly right. So actually there is a paper from Arnold Zellner, 1989, and the American statistician, where he basically shows that the optimum way to update information under the assumptions I started the talk with is exactly the KL, or the log likelihood. So it's exactly right what you're saying. You're replacing what would be statistically optimal under the well-specified setting with something that is not as efficient statistically, but gives you robustness. So you're losing if the model is well-specified, but the loss is somewhat asymmetric. So not this loss. I mean, what you're losing is asymmetric. You're losing a lot if you use the KL or the log loss in the presence of outliers, because it's very sensitive to that. And you're losing, hopefully, comparatively little in statistical efficiency if you use a robust loss instead. But that quantification, that is actually very explicit in the frequentist literature, and we haven't developed that yet. We're in the very early stages of this, actually. Yeah.
So I had a question, unless the online audience has a question as well. So if so, I think you should be able to unmute yourself and ask, and we should hear you on the speakers. Maybe let's wait a second, or the online audience can think about questions while I ask mine. So here you tapped into the existing literature of losses and discrepancies and showed that some are useful in terms of robustness. Do you think the theory would allow you to also come up or design new losses actually from scratch, or more from scratch, than tapping into the existing ones?
So this kind of ties into what Nicola was asking about. This theory, no, because it's like a binary yes-no decision. So which is why this is extremely limited. Like you can do this with the frequentist stuff. So that stuff is like super advanced, and we need to, I think, borrow a lot from that literature. It's obviously more complicated because you're dealing with measures. So you need to translate a lot of things that were constructed for Euclidean spaces into measure spaces. It's a bit tricky, but that would be the dream if we could do that. I think that would be very interesting because it would allow you to much more, like that's actually one of the unresolved questions as well in general, is how you pick a loss. I mean, if I give you a Gibbs posterior, I don't just give you a model selection problem, I also give you a learning selection problem, right? So one of the beautiful things about the Bayes posterior is you just pick, it's hard enough to pick the model. I've made the problem harder. You now also need to choose how you want to learn from data. I think that problem is surmountable, but it's not easy. I think we'll need years to get there.
So any voices from the online audience? If not, I think we can just stop here, and we look forward then to the second half of the talk. And let's thank Jeremias for the awesome talk.